Dear listener, today we talk about our unexplained mysteries of the universe, so please listen carefully. The universe is a vast, enigmatic expanse that has captivated humanity for millennia. From the twinkling stars in the night sky to the incomprehensible depths of black holes, the cosmos is filled with wonders that challenge our understanding of reality. Despite centuries of scientific progress, many questions remain unanswered, leaving us in awe of the mysteries that lie beyond our reach. This article explores some of the most profound and unexplained mysteries of the universe, inviting you to ponder the secrets of existence. 1. Dark matter and dark energy, the invisible forces. One of the greatest mysteries in modern cosmology is the nature of dark matter and dark energy. Together, they make up over 95% of the universe, yet they remain invisible and undetectable by conventional means. Dark matter is believed to provide the gravitational glue that holds galaxies together, while dark energy is thought to be responsible for the accelerated expansion of the universe. Despite decades of research, scientists have yet to directly observe these elusive components. What are they made of? How do they interact with the visible universe? These questions continue to baffle researchers and drive cutting-edge experiments. 2. The Big Bang. What came before the Big Bang theory is the prevailing explanation for the origin of the universe, describing how it expanded from an infinitely hot and dense state approximately 13.8 billion years ago. But what caused the Big Bang? What, if anything, existed before it? Some theories suggest that our universe is just one of many in a vast multiverse, while others propose that time itself began with the Big Bang. These ideas remain speculative, as they push the limits of our current scientific understanding and technological capabilities. 3. Black holes, the cosmic abyss. Black holes are among the most fascinating and mysterious objects in the universe. These regions of space-time are so dense that nothing, not even light, can escape their gravitational pull. But what happens inside a black hole? At its center lies a singularity, a point where the laws of physics as we know them break down. Additionally, Stephen Hawking's theory of Hawking radiation suggests that black holes can evaporate over time, raising questions about the fate of information that falls into them. The study of black holes continues to challenge our understanding of gravity, quantum mechanics, and the nature of reality. Observable universe, the things we are able to see or calculate using a computer model was called the observable universe, and the things that we can explore within it are known as the metagalaxy. So where are we within this system? Let's have a look. There's our home, planet, Earth, and the solar system. The solar system is a part of the local stellar system along with the neighboring stars and their systems. We are part of the Milky Way galaxy. The galaxy itself is part of a larger group of galaxies. As we zoom out even further, we can see our place among other galaxies in the Lang supercluster. Seems huge, doesn't it? The final reference for scale will be the observable universe. In the grand scheme of things, we are only a tiny grain of sand, but even an entity of this size has its limits. We're facing the fundamental question. Everything that we see, is that the extent of the universe? How can we see beyond the light emitted by stars? Take a closer look at the map of the cosmic microwave background. The brighter spots signal the changes in temperature and space, which signifies where the star systems, galaxies, and supergalaxies can be found outside of our visual range. Is it possible to use relic radiation to see the entire universe? Think about the night sky. If you're on a brightly lit street or next to another source of light such as a campfire, it's difficult to make out the faraway stars in the sky. Same principle applies here. Relic radiation illuminates the universe and all its glory. However, its light also hides the dark alleys of the universe. For example, the areas devoid of stars. It also hides black holes in places in our universe that have not yet been reached by light. Remember, the consequences of the Big Bang are still relevant. So is there anything beyond this edge? It seems that the answer to this question was found through the inflation theory. According to this theory, the bounds of our universe continue to expand at a rapid exponential pace, which leads to a conclusion that the universe cannot have a concrete boundary. Let's circle back to that piece of paper. You crumbled at the start. Has it begun to unravel yet? It's obvious that sooner or later it will come back to being the same size as the sheet you grabbed initially. The most elementary physics dictates that the inflation theory has its issues because the laws of physics work in the same manner in every part of our universe. Even though scientists found countless things that confirm the rapid expansion of the universe after the Big Bang, as well as plenty of facts that suggest continuing expansion, that's far from being the big picture. Think about your piece of paper. After all, without the force from your hands, nothing could have happened to it. For almost 80 years, this model was set aside as a false theory, but at the beginning of the 21st century, it was brought back from the dusty shelf to Princeton. Scientist Paul Steinhardt and Neil Turk have come up with a completely new version of it. Their model is primarily based on string theory. It is rooted in the idea that everything material in the universe consists of tiny particles which collectively make up something roughly similar to strings. For example, the smallest particle of light is called a photon, and it manifests as rays of light made up for many of these particles moving in a certain direction. We see this movement as light. Same principle applies to sound, gravity, heat, and so on. According to their theory, there is no beginning or end of the universe. There's just endless strings of matter that interact with each other according to their scenario. The history of the universe is an endless cycle, but in this case, instead of starting a new universe, it denotes the next phase of its existence. According to their model, our universe emerged as a result of a collision of two three-dimensional worlds. So why can't we see this neighboring world? According to string theory, in addition to the three-dimensional world visible to us, matter exists in several additional dimensions, and so it's not unreasonable to theorize that two three-dimensional worlds could collide within the framework of an additional hidden dimension. String theory suggests there could be up to 50 dimensions in which matter exists. As these three-dimensional worlds collide, they stick together and the kinetic energy from the impact is converted into quarks, electrons, photons, and other simple elements of matter. In turn, this process generates the energy for the expansion of our universe, and so two colliding worlds give each other energy. This event gives rise to life in one of them, but in the end, our universe has a certain limit of both expansion and life as we know it. Over time, it will return to its normal state. After all, the energy that fuels expansion will come to an end and then the reverse process will begin compression. For the Fermi Paradox, where is everyone? The universe is unimaginably vast, with billions of galaxies, each containing billions of stars and planets. Given the sheer scale of the cosmos, it seems statistically likely that intelligent life exists elsewhere. Yet, despite our best efforts, we have found no evidence of extraterrestrial civilizations. This contradiction is known as the Fermi Paradox. Are we alone in the universe, or are advanced civilizations hiding? Possible explanations range from the rarity of intelligent life to the idea that advanced civilizations self-destruct or avoid contact with less developed species. The search for extraterrestrial life remains one of humanity's most profound quests. 5. Cosmic inflation and the universe's structure. In the first fraction of a second after the Big Bang, the universe is believed to have undergone a period of rapid expansion known as cosmic inflation. This theory explains the uniformity of the cosmic microwave background radiation and the large-scale structure of the universe. However, the cause of inflation and why it stopped remain mysteries. Additionally, the universe's web-like structure of galaxies and voids raises questions about the initial conditions that led to such patterns. Understanding cosmic inflation could provide insights into the very fabric of space-time. Since Pluto lost its planet status, scientists have not abandoned their attempts to detect other large objects on the edge of the solar system. After all, there is something beyond the orbit of Neptune that significantly affects the trajectory and revolution of celestial objects like asteroids and dwarf planets. And this isn't the kind of something we can detect with telescopes. Recent research suggests it could be a miniature black hole or even a cluster of dark matter. In this video, we'll examine the mysterious ninth planet. Its properties, size and whether it is a planet at all. The question about the existence of the ninth planet became especially prevalent when scientists closely studied the movements of trans-Neptunian objects in the Kuiper belt, an area on the edge of the solar system similar to an asteroid belt. Astrophysicist Konstantin Batygin and Michael Brown studied 6 distant objects in the Kuiper belt, dwarf planets and planetoids, including the dwarf planet Sedna. They found that the objects followed elliptical orbits pointed in the same direction, but moving at different speeds. This was a rather unexpected discovery, and Brown even made this analogy. This kind of result is if there were a clock with 6 hands moving at different speeds, but as soon as you look up, all the hands are in the same spot. Brown implied that this type of event is very unlikely, and on top of that, the orbits of these 6 objects are tilted at the same angle, about 30 degrees downward in the same direction relative to the plane of the 8 known planets. The chance of this happening is about 0.007%. The first proposed theory was the presence of certain objects near the borders of the Kuiper belt that would affect gravity. Therefore, if that were the case, the mass of the belt should have been 100 times greater than it is today. Computer simulations using a small planet have shown that its mass would be insufficient to align objects in this manner. However, if you run a similar simulation with a massive planet the scale of Uranus or Neptune, the mathematical model converges and practically duplicates the real-world calculation results. The work of Batygin and Brown sets limits on the possible mass of the ninth planet, the location of its orbit and its position in the sky. According to calculations, the mass of the planet is 5 to 20 times greater than the mass of Earth, and its diameter is 2 to 4 times larger than our planet's. To see this planet directly through a telescope is almost impossible. It is too far to register in our visible spectrum, so we have to search for it using its faint infrared glow. However, with a mass of only 5 Earth masses, it wouldn't give off much heat. Additionally, such a distant planet would revolve around the Sun very slowly, so it would be impossible to detect its movement. Although Batygin and Brown actually prove the existence of a certain object that influences the position of other celestial bodies, recent research conducted over the years 2020 to 2022 have cast doubt on the existence of a massive planet. In a relatively recent study from 2021, critics of the Batty-Brown theory have about 300 new objects in the region of the Kuiper belt where the Batygin and Brown theorize the presence of the ninth planet. Astronomers scanned the better part of the sky with the 20-foot A space telescope in Chile in search of the new planet and spent 6 years studying 87% of the sky accessible from the southern hemisphere. Reportedly, a detailed examination of the orbits of objects in question revealed that every case of orbit synchronization can be explained by known physics effects except for 2 celestial bodies, but even these 2 anomalies are an exception out of 300 objects, and in a way they confirm the new theory. Why do discoveries in these orbits not coincide with Batygin and Brown's predictions? The answer may be that the ninth planet theory is simply incorrect. 6. The nature of time. Time is a fundamental aspect of our existence, yet its true nature remains elusive. Why does time move forward? Is it an illusion, or is it a fundamental property of the universe? Theoretical physics allows for the possibility of time travel through wormholes, But are these ideas feasible, or are they just mathematical curiosities? The study of time intersects with cosmology, quantum mechanics, and philosophy, making it one of the most intriguing mysteries in science. It is not yet possible for us to comprehend the size and shape of the heliopause. The best way to envision the heliopause is located in your kitchen or bathroom. Turn on the tap and take a look at the place where the water hits the bottom of the sink. The area where the water is flowing along the surface of the sink is interstellar space. The place where the water disperses due to the impact is the heliosphere. The thin border where the falling water runs into the flowing water is the heliopause. Scientists divide the heliopause into a bow shock, the place where interstellar space scatters about it, and a main shock wave where the solar wind is slowed down by the impact of interstellar space. What does the heliopause look like? Thanks to the traveling probes, we know much more about it now, but still not enough. Voyager 1 and Voyager 2 crossed the heliopause at different points located a different distance away from Earth. It showed that the resistance was different at varying exit points as well as other conditions. And here's another bit of nuance. For a long time Voyager 1 couldn't even definitely prove to the scientists that it had crossed that border. Where are we as we fly through space with our heliosphere? We are within an interstellar cloud around us, several similar clouds. Right now, we are approaching the edge of our native cloud. It is throughout its existence within this cloud that it became the solar system as we know it. In 3,000 years, we will exist in new conditions in the so-called G-cloud. It won't happen anytime soon though, because even with our speed of traveling through the galaxy, there's still a huge distance we must cover to leave our native interstellar cloud. Who knows, perhaps in a few thousand years it is not only our appearance that would change. By then the solar system may be much less habitable. The actual crossing of the heliopause by the Voyagers has been a subject. Many arguments. It's no joke. NASA announced that the Voyager 1 crossed the border between the solar system and the great cosmos only on the 12th of September, 2013. That's 13 months after the discovery of the fact and rigorous checking of this information. The probe had actually crossed the heliosphere on the 25th of August, 2012. So how did they know that it happened? The experiment showed that the very hot particles present in the solar wind are gone. On the contrary, the cosmic radiation, the traces of the influence of surrounding star systems, extinct stars, our recent neighbors had increased. However, many researchers were not convinced about these findings and they had their reasons for it. Firstly, the piece of equipment responsible for an extensive analysis of particles emitted by the Sun and other stars stopped working on Voyager 1. More precisely, it was a plasma device. Secondly, the scientists do not expect that the magnetic field on the constraints of the solar system would be pointed in the other direction. But that didn't happen. We still don't know why. To this day, it is unclear why the magnetic field outside of the heliosphere is the same as the magnetic field within it. But in 2012, solar storms swept through our solar system. Voyager 1 sensors recorded these changes in the space weather, and their readings proved that the probe did indeed cross the bounds of the system. As the echoes of the storms collided with a much denser environment than that in which Voyager had previously been. That is, the probe was already outside our heliospheric bubble, whereas the crossing of the heliopause by the Voyager 2 went much smoother. Its plasma device was in working order, and it registered the crossing in 2018, simultaneously confirming the data recorded by its sibling. 7. Quantum mechanics, the weirdness of the subatomic world. Quantum mechanics governs the behavior of particles at the smallest scales, but its implications are anything but small. Phenomena like wave-particle duality, where particles behave as both waves and particles, and quantum entanglement, where particles instantaneously affect each other across vast distances, challenge our classical understanding of physics. These strange behaviors have led to debates about the nature of reality and the role of the observer in shaping it. 8. The fate of the universe. How will the universe end? Scientists have proposed several scenarios, including the heat death, where the universe expands forever and becomes cold and dark, the Big Crunch, where the universe collapses back in on itself, and the Big Rip, where dark energy tears the universe apart. Each scenario depends on the balance of forces in the cosmos, but the ultimate fate of the universe remains uncertain. Conclusion. The universe is a place of infinite wonder, filled with mysteries that push the boundaries of human knowledge. From the invisible forces of dark matter and dark energy to the enigmatic nature of black holes and time, these questions remind us of how much we have yet to discover. As technology advances and our understanding deepens, we may one day uncover the answers to these mysteries or perhaps discover even more profound questions. Until then, the cosmos remains a source of inspiration, curiosity, and awe, inviting us to explore the unknown and marvel at the beauty of existence. Please like, share and subscribe my channel for support me. Thanks from Relax Audiobook.